A problem with a lot of the current alignment methods is that the evaluation structure that they learn, what defines what counts as good or safe behavior, is tightly entangled with the policy itself. So this objective is very dependent on the policy itself. And once that's happened, the step where we try to assure that this structure behaves well becomes mostly passive. Because we can observe failures, gather data, and maybe learn how to retrain the model better. But actually fixing it means often doing a lot of the work over again. We often have to relearn the reward model from scratch, for example. What we propose instead is to preserve this evaluation structure in a standalone artifact, which is learned separate from any policy. Then failures don't just become signals from another training run, they become inputs for an active loop around the artifact itself that lets us audit it, verify the problems in it, refine those problems, and then redeploy it, and do this in a loop. That's the shift from alignment waste to durable alignment. So how do we actually get an artifact like this? That is where we introduce interactionless inverse reinforcement learning. Instead of using a policy to learn how to create these evaluation artifacts, what we do instead is we take expert data and optionally some negative data or constraints, and we use this to construct an evaluation artifact from data itself. We don't use any policy or environment interactions at all. This gives us a few important properties. It's portable. We can use it across different models or contexts because the artifact itself is verified on a global scale and is not optimized for a specific policy. It's expressible. We can actually look at what it has learned and audit a lot of the cases to check if it's actually correct. And importantly, it's edible because we have this fixed object. We can make sure that we can patch some flaws before we can actually deploy it. So interactionless inverse reinforcement learning gives us the object that we want. We have a decoupled evaluation artifact that we can reuse and we can reason about. But now, how do we govern this artifact? And our answer is a multi-agent system, but more importantly, a human-in-the-loop multi-agent system. The alignment flame is a structured system where different agents take on different roles around the artifact. Some agents audit the artifact to try to find useful observations, to discover potential flaws. Others verify whether those cases are actually real flaws or violations. Then a triage agent gets a queue of all these cases and decides which one have the highest priority to get fixed. And then you have refinements agents, and they reason about which kind of patches should we apply to the model to solve these flaws in the model. Then afterwards, we have another step where these patches are actually tested in a sandbox environment to make sure that the patches actually don't have negative impacts. Depending on the ethical requirements of this specific use case, scalable human oversight is in place. So at each of these steps, you can choose how much oversight a human should have. You should enforce that a human should oversight every single decision, or that it just has to approve the patches at the end. It is up to the use case as itself. Since we made the paper, we've also started operating a small-scale experiment of this, of a working version. So here's a simple example. So there is an expert bars in blue, and the artifact has learned that it says good behavior, so it knows that it should get high rewards. But in this flood model, you can see that there are high rewards far outside of the region in the corner of the grid. And we don't want this, so we want to fix this. So now we will let the alignment flywheel model run, and you will see it will improve. What you're seeing now is an artifact being refined over time, and each red cross means a flaw being found and patched by the model, and over time you see that it becomes more and more clear that we only focus on the regions closely around the expert paths. This is only a small case experiment, but it shows that the alignment flywheel is not just a blue sky idea, but it's already starting to be working on a small scale. So to wrap up, the goal here is to think about what does alignment leave behind. Many of the current alignment methods throw away all their work right after training one model. So we believe first alignment should become a durable engineering asset, not just something that disappears into a single training run. Second, alignment knowledge should be portable. If we learn something from one model, we should be able to port it to a different model without many retraining. And third, we want to move away from passive oversight from these alignment models and create more of a life cycle. So if we want to make alignment less wasteful, it has to become something that we can keep, reuse, and fix.